Hello.
Hello.
Philip told me to tell him that we should tell him that we have like some people have tech issues, so we can ask permission to record as well. So I'll let him know that when he joins.
All right.
Aruz, do you have like an intro thing prepared, or are you just gonna wing it?
Yeah, I have like an intro prepared.
Okay.
I'm ready. Mhm.
Wait, should I call you Aruzan or Aruz?
You could call me, I don't know, any variant works really.
Okay. I'll just say Aruzan because that's what it says in Zoom.
Okay.
Hi, Dr. Gladney.
Hello.
Uh, Before we begin, I just wanted to let you know that like a lot of people are having tech issues right now. So is it okay if we record this meeting to send out later? We also have like a live stream on YouTube, where a majority of our audience is, but we just want to ask like it's okay to record the meeting.
Sure, no problem.
All right, thank you.
And you can
Recording in progress.
let me know when to start. So
Okay, so hi everyone. We are super glad that you are taking part in our speaker series event today. And joining us today is Dr. Larry Gladney, a professor in physics and Dean of Science at the Faculty of Arts and Sciences of Yale University. Dr. Gladney works at the intersection of experimental particle physics and cosmology. And also his research focuses on the fundamental connections between matter, energy, space, and time. Today, Dr. Gladney will be giving a presentation on the Legacy Survey of Space and Time. And if you guys know, it's a 10-year sky survey that is aimed to evaluate like answers on dark matter and dark energy, and many more. So I'll hand it off to Dr. Gladney from here. And also, just to remind, we'll be having a Q&A session at the very end.
okay, thank you. About how long should I give a presentation?
I mean, it could be as long as you want. I think average might be around 30 minutes or so, but if you want to go longer or shorter, that's perfectly fine as well.
Okay, so probably a little longer than 30, but I'll try and keep it to around that time. First, thanks for inviting me. And second, if people have questions, we'll have a question and answer session at the end. But if you want to raise your hand because there's something immediate, just let me know. We have to stop and answer questions. So first, let me see if I can share my screen. Hopefully you can see that. Is that okay?
Yeah,
Great.
looks good.
Terrific. So I'm going to talk to you about the things that are most interesting to me and that I've been working on literally for the last roughly almost 20 years now. It's 18 years, but it's basically a story which we want to get out to the public that's not complete yet. And those are always kind of the best scientific stories, the ones for which we have a real expectation that there's an exciting answer. But it's not clear yet exactly what the final chapter of that is going to wind up being. And it's why we spend so much time trying to actually hone the technology to get to the point where we can actually describe something that in the end is beyond our ability to describe right now. And this has to do with understanding the most fundamental aspects of the universe as a whole by looking at the very simplest pieces of it, that is, the most fundamental building blocks and how those go together in order to make physical reality as we see it. So I was told that I was supposed to try and make this a bit personal in terms of my motivations for it. And so I'll just say that I've wanted to be a scientist since the age of 3, and I understood at the age of 12 that science had to be physics. I wasn't quite sure up until that point because most of the science you get introduced to, at least in first grade through 5th grade, is biology and a lot of chemistry and things like that, and not so much what we typically think of as physics, which is how the universe works at a mechanical level. But I had these big unanswered questions, and it was really in 7th grade, right at the beginning of the school year, when I discovered that physics was the only approach that was likely to be able to answer any of these. Now, that means, of course, that I had been convinced that physics was the right way to go. And the reason for that was that a bunch of other questions, which were much more common, I had understood by that point in 7th grade, had already been answered by physicists. So things like, why is the sky blue? Why does the moon appear in phases? From a quarter to a half to a whole, and then going back over the course of 28 days. where the tides come from. A lot of these things I had realized had been answered by physicists. Most of the work having actually been done centuries before, Newton, of course, being a big contributor to those. But there were still these other questions that were left, and it was likely that physics was going to be the most salient science in order to understand those. What is the world made of? How do you put it together? Does time have a beginning? Does it ever end? Why does math work so well? Like, I was interested in math, but it always seemed to me to be more of a game. And I understood that there were real equations that you could put information, measurements from the past into the equation, and it would actually predict the future. And the question is that actually something that we could expect would work to answer these questions that are at the top of the page? And then finally, at the end, is it actually possible for people to understand everything about the physical world? Or are there going to be mysteries that we just can't get answers to, or can't understand the answers to, even if we have some way of exploring them? And that last question was really particularly pertinent for me because I grew up in a very religious family, and it was really around the ages of 11 or 12 when I kind of rejected religion as a way to answer these questions and just gave up on the idea that it would ever actually come to something satisfactory for me. Now, over time, between 7th grade and 12th grade and starting college, I realized that those questions had to be formulated in a slightly different way to be something that we could actually directly measure or observe. For example, what is matter made of? What are the fundamental parts or building blocks of matter? Why is gravity so different than the other 3 fundamental forces in the universe? Why does time flow in only one direction when, in fact, we understand at the very smallest levels that time actually doesn't have a direction? Physics is agnostic about the direction of time. But of course, at the level at which we interact with things, we only go from the past to the future and never back. How did the universe begin? Does it have an end? Is there a unified theory of fundamental physics? These are the things that actually are necessary to answer the questions on the previous slide. But it starts with the last question on that first slide, which is the universe itself understandable? And so again, it was around the age of 12 or so where I actually understood that physics included another subject called cosmology, and cosmology had actually posed this question and come up with an answer that was, at the time, again, much more satisfactory to me personally than answers that I had heard to similar kinds of questions that were asked around religious religious understanding. And so the question is, can we understand by observation how the universe works as a whole? And the answer is that it's a possibility, but it's only because the universe, as vast as it is, shows certain characteristics which can be put into a unified picture. That is, you don't have to understand how everything works at the same time in order to understand how everything works at the same time. And what I mean by that is that you can look at a part of the universe, you can see that there are rules, you can understand what those rules are. And when you apply them to another observation of another part of the universe, really far removed from the first part that you looked at, you find that the rules are completely the same. They operate in exactly the same way. They give you the same predictions for what you're going to see in a third part of the universe if you kind of say, here are the characteristics that I expect to be able to observe. So there is diversity. If you look on small enough parts of the universe, you actually do see that there's slightly different ways in which things are happening. But the underlying basic rules, the really fundamental rules, are exactly the same, again, from place to place to place. This was really made known to us in the most serious way by Newton. It's called the Newtonian synthesis. And it's the basis by which Newton said, I can do experiments in my parlor on a tabletop that actually can apply to the entirety of the universe. So it's an apocryphal story. We don't know whether it really happens, but he did grow up on a farm, and he did say that he understood how the moon must be in orbit around the Earth due to gravity by watching apples fall from a tree. And so the idea that you can simply take an observation of how something is falling due to gravity on Earth and apply that to how the moon falls around the planet Earth and come up with a prescription, an equation, which works precisely. And he, in fact, did that calculation in his head to say that if I know how long it takes the apple to fall from a certain height to the ground, I can determine why it is that the moon takes exactly 28 days and 12 and a half hours, to be more exact, to fall around the Earth. And that also explains why we get this repetition of the phases from month to month to month. And so it was really clear to me at that point that Newton, followed on by Einstein 2.5 centuries later, who had worked out the path for why it's physics that's able to answer these fundamental questions that I had in my mind. That is, that we have a reductionist path. That is, you only have to study a really small part of the universe in order to get some of the rules that actually apply to all of the universe. And then as you start increasing the size of the universe that you bring into the set of rules or equations that you're using, in fact, you do have some hope that there are going to be eventually some universal laws that work exactly the same way at all scales, from the small scales to the very largest ones. So that's been the progression and the history of physics from the time of Galileo and Newton through the time of Einstein and literally up to today. And so consequently, there are two specialties within physics that actually discover the rules that apply on the smaller scales and on the very largest scales. They're called particle physics and cosmology, respectively. And particle physics is, I was on the committee that helped define this, around 2003, which is particle physics is described now as the science that understands the nature of matter, energy, space, and time at the most fundamental level. And cosmology came along, as I said, as I pointed out, actually in the early 1900s, to be the science that talks about how the universe came to be, what the correct description of it is now, and how we predict what its future will be. And the way in which we understand that is by looking at the interactions, again, of energy, matter, space, and time. So it was really only around the 1980s, I got my PhD in 1985, when this really came into full blossom for both of these, and the connection between the two became very apparent. That is, that we have to understand the rules that operate at the very smallest level in order to understand the rules that happen at the very largest scales, and vice versa, right? Because it was also in the 1980s when we realized that if we could study how nature operates on the very largest scales, that's a way to get at how things are happening on the very smallest scales, that we don't necessarily have the technology to do the experiments that we want to answer the questions about what those interactions between matter, energy, and space and time actually are. And so these two subjects, which look like they talk about very different things, right? Something that operates at the smallest level, something that operates at the very largest scales, actually communicate with each other very effectively. And consequently, the technology that we needed to do the experiments that would answer these fundamental questions that we had in mind for particle physics and for cosmology all had a common origin. That is, what we could build the same instrument to attack questions at both scales at the same time. Now, by and large, that might seem to be a very esoteric pursuit, something that is interesting to scientists, but not necessarily interesting to everybody else. But there is a very practical outcome for this, which I do want to remind people of, which is that every time that we study these really fundamental questions in the past, it's always led to technologies that we now see as absolutely essential. We don't know where they came from. We don't bother to understand what the history was by how we came to them. But they are just such parts of our lives that we can't imagine having life, and certainly not the way that we do now, without these technologies. But cell phones, GPS navigation, which I have in my car, and that's how I found my way to the place where I am right now to give this talk to you. The World Wide Web came out of particle physics. Televisions came out of basically particle physics in its earliest forms, which was nuclear physics, but the technology that was necessary to do those experiments made it possible for a physicist to define and design the very first color television set in Berkeley in the early 1950s. And cancer radiation therapy, all these things actually came out of people trying to answer the most fundamental questions of their time and finding that they needed to develop technology in order to do the experiments that were necessary for the observations. And then it turns out that those very same technologies can be applied to these very practical concerns right now. So it's very likely, because it's been the history, there's no reason to think that it would change now, that these very fundamental questions will lead us to do experiments that in turn will have really profound effects on technology for the future. We don't know what those are. They're probably decades away, but it's almost inevitable that we will see them. All right, so what are the experiments? They began with trying to understand where we are in our understanding of how the universe was born and how it evolved from the state of birth to where we see it now. And so those experiments having been done over the last 60 years. Sorry, was there a question?
Oh, my bad.
Okay, so for the last 60 or 70 years or so, those experiments have pointed to a really consistent and, again, unified picture. That is, we could look at really different scales, but we see the same hints leading to the same picture, which is that the universe began at a very hot state from a very small scale, much, much smaller than the scale that we see right now. And the reason we know that is because we can see the heat from the birth of the universe that's still around everywhere, coming at us from every direction. And because the characteristics of it are so uniform, we can actually tie that to the beginning of the universe as the only way in which, if you think about it, because the speed of light is finite, there's no piece of information that can get to us if it started from a different part of the sky than another part of the sky. And therefore, we wouldn't expect to see the same thing if we look in different directions on the sky. But this radiation, which is, as I said, leftover heat from, we now term it the Big Bang, seems to be what we call primordial. That is, it's among the first things that there was. And the question of what else is primordial is that we see these things called quarks and leptons. The names of them don't really matter, but the fundamental building blocks of any kind of substance, you and everything around you, is made of atoms. Those atoms are made of protons and neutrons and electrons. The protons and neutrons are made of still smaller things called quarks. And so it's the quarks and the electrons, plus some other things that are very similar to the electron, but much heavier, which make up all of the building blocks of matter that we see. And so any piece of matter that we've ever seen anywhere in the universe seems to have the same physical characteristic, indicating that these so-called quarks and the leptons, like the electron, are the fundamental building blocks. Now, what I'm showing is a very neat picture that, again, comes from 6 decades of experimental study. And it looks as though it's pretty complete. And it is, but only within the context of a theory that we actually understand is incomplete. One of the reasons we know it's incomplete is that it does not include what's on the right-hand side, as you can see over here, which is gravity. Okay, and so the question of why it's incomplete, that takes a whole hour to go through, but we do have pretty firm evidence that, in fact, we do have the fundamental building blocks, but there probably are more than is included in that picture on the left. One of the reasons we know that is that the universe as it currently exists can't exist if those building blocks are all of the matter that happens to be out there. And I'll explain how we know that there has to be other kinds of matter available in the universe than can be made from those building blocks. But essentially, the idea is that the universe can be tracked back in time, because the further out we look, the further we the further the sources of light are from us. And since light does take a finite amount of time to travel from its source to where we observe it, detect it and observe it, we are essentially looking into the past. And the further out we look, the more into the past we are actually seeing. And that tells us a picture, when we look as far back as we can see with the most powerful telescope, of something that's pretty profound. So the first is that we can actually see evidence that particle physics determines the script of the universe from roughly around, if we use exponential language, 10 to the minus 14 seconds to about the first 3 seconds. And then from the first 3 seconds to the first 3 minutes is nuclear physics. And then from the first 3 minutes to the succeeding 13.5 billion years is gravity, plasma physics, and hydrodynamics. Okay, so we can put together a pretty complete, again, through equations. We can put in information for measurements, and we can make predictions about what the past would have looked like. And then we can actually go out and use telescopes to look into the past and see that it matches exactly what we would have predicted. So the idea about how we build up our picture of how the universe began and how we know that these theories of physics work is that we simply have to determine where we are today in terms of observation, make predictions on the basis of the physics that we understand must have been happening or should have been happening in the past, then do an observation into the past. And we see that, in fact, at every epoch, we actually are able to predict pretty well what the universe looked like, back to literally the first 400,000 years or so. And then when we look at and we can't see back further than that in light, because at that point, the universe was so hot that, in fact, there was no cohesion, right? There were things like atoms, but they were constantly being blasted by radiation. And there were no stars to emit light, for example. And so to look further back than that, we have to look at what was happening in that first 400,000 years for evidence of physics that was happening in the past. And again, that physics is predicted by particle physics theories, and we can understand that what we see in that first 400,000 years or so, 380,000 years, happens to actually reflect quantum processes, that is, things that were happening at very, very small scales and very energetic scales that were happening at still earlier epochs. And that all fits up until the point where we get back now to roughly 10 to the minus 30 seconds. So somewhere in the first billion trillionth of a trillionth of a second, we have the physics. It works extremely well for all of the data that we have. And beyond that point, we actually have just a mystery, right? We don't understand what the physics is that applies before that. So as I said, what is this evidence that we have that allows us to get beyond 400,000 years where we don't have actual direct light to see? Well, again, we have a picture of the universe. This is a baby picture at roughly 380,000 years after the beginning of the universe. And you can see that it's not uniform, right? There are red spots and there are blue spots. And the blue spots tend to congregate together and the red spots tend to congregate together as well. Well, that pattern is, in fact, quantum information. We expect that we would see a picture that looks similar to this one on the basis of what particle physics predicts, simply on the basis of the fact that particle physics follows the rules of quantum mechanics. And quantum mechanics predicts that at the very smallest scales in which the universe had to be operating in order to have a picture that was this hot and this energetic. In fact, those quantum rules predict how large those red blotches are and how large those blue blotches are. And the experimental measurement of how large they are matches exactly with what we see. Now, it's also the case that the universe must have been expanding, and as it expands, it cools off. And as it cools off, things start to come together once we're not so hot anymore. So within the first billion years, in fact, we're seeing even further back into the past now, before that billion years with the James Webb telescope, we see structure, we see clumps, and we see voids. And this is due to the fact that gravity, once things are cool enough, is able to actually pull stuff together and have it stick so that we can make a clump. And it does that by pulling this out of areas where there was matter, and so we now have voids. So the question of what happens now, as we say, depends on the resolution that we actually apply to this picture of the hot radiation that comes from a Big Bang explosion. So in the first instance, we were able to take pictures in which we could measure the temperature at various parts of the sky to parts in 1,000. And so what you see is this very red picture. This is actual data that shows the picture of the universe again at the first 400,000 years. And it shows that the temperature is really, really uniform to a part in 1,000, just a few degrees above absolute zero now. But back 13.7 billion years ago, this was literally billions of degrees. But we can see that it was really very uniform. As we start to look with more resolution, we start to see that there are astrophysics effects. And so this middle picture, which we have blue blotch on the bottom and kind of an orange red at the top towards the right, that is because our galaxy is moving with respect to the rest of the universe. And so what we're seeing is a relativistic effect here, right? We're seeing that it's slightly hotter in one direction, and that's because we're moving in that direction. So we're intersecting the radiation that's coming at us. And we're leaving behind the radiation that's coming from the opposite direction. And so that looks a little bit cooler, which we represent with the blue color. At about a part in 100,000, then we see the picture on the bottom. That red part is due to dust for our galaxy, so that's still an astrophysical effect. But those other blotches are the quantum fluctuations that I talked about earlier, right? And so those are cosmological effects that are showing up. That again matches exactly what we expect from our theory, assuming only quantum rules. We don't have to know the details of the physics. We simply have to assume that whatever they are operating according to quantum rules. And we get a picture that looks pretty similar to the one that's shown here from an image of the universe that was taken by the Planck satellite operating in orbit around the Earth around 2013. Okay, now that tells us what was happening in the first few moments of the universe's history. How do we get a picture of everything that's in the universe now? Telescopes, we have good belief now, strong belief now, doesn't actually tell us the existence of everything that currently is out there. And that's because we have the ability to understand what gravity is doing to the things that are emitting light. And we can see that, in fact, there's not enough gravity to explain the behavior of all the things that are emitting light. As we go further and further back into the universe's history, the discrepancy between what we would expect to see, assuming that all that there was to matter was, again, quarks and leptons and atoms and molecules, is not complete. That's because gravity responds to all forms of matter and all forms of energy, right? And so it's a very different picture than the one that we had with Newton of what gravity does. But in Einstein's theory of gravity from 1915, what he says is that we can actually see the effect on space and time of matter and energy through gravity. And that's because gravity warps space, and matter and energy in moving through space over a period of time will see the changed shape of the space by changes in their motion from what we would otherwise expect to see that motion to be. One of the ways it does this is in what's called the cosmological redshift. That is, as the universe gets bigger, any light that is actually existing in the universe gets stretched along with the universe. So let's say that there is a galaxy that is 1 billion light years away from us. That means it's going to take 1 billion years for the light to get to us. In point of fact, it's going to take in actual time something closer to about 3.5 to 4 billion years to reach us. And that's because the distance between us started at 1 billion light years from the source to us. And over time, the universe has gotten bigger by about a factor of 3.5 in that time. And therefore, the light has taken about 3.5 times longer to get to us. But it's also the case that the light itself gets stretched along with the universe. And consequently, the light is also about 3.5 times longer in wavelength than it would have been if the universe was not growing. So that's a very real effect that happens because space and time are changing along with the evolution of the universe that we can see directly. And the rate at which the universe gets larger and larger, coming from this initial explosion that throws everything outwards, is an effect that we can see as well in the redshift. That is, the gravity of everything ought to be slowing down the rate of expansion. And consequently, there's a difference that had there not been gravity slowing things down, we might have expected it to be 4.5 times larger than it was at the time that the light was emitted a billion light years away from us. And we don't see that effect. So here's a direct effect in which gravity has to be included correctly in order to explain the redshift of things in terms of their distance. So the Hubble telescope and now the James Webb telescope are the most powerful telescopes we have in terms of seeing things that are very far away. And the cosmological redshifts that we measure are consistent, again, with what we expect for a universe which is expanding, but in which the rate of expansion has been changing over time. Okay. Now, another way that we can see the effect of gravity is that it distorts light. It distorts the shape, therefore, of light. It acts like a glass lens. It can actually bend light, which would otherwise travel in straight lines. And that bending is what leads to the distortion, like with a funhouse mirror. Or if you have a telescope, you might notice that if it's a cheap telescope, it actually changes the shapes of things. It doesn't simply make them bigger. And consequently, we can see the picture on the right here on the basis of something that started with the left as the source of light gets distorted. And so if there's something that's very massive, emitting a lot of gravity in between us and this background image, then in fact, what we get is a distorted view like this one. And consequently, we've now determined through math that we can see how much stuff is emitting gravity, that is, how much gravity there is by looking at the amount of distortion, even though we don't know the shapes of the things intrinsically. That is, that's how well math works. Statistics tells us that even if we have a random set of shapes, like galaxies, we can actually look at the distortion from the kinds of galaxies, the shapes of galaxies that are close by, and we can determine how much gravity there is between us and the background galaxies that are further away. So we can see stuff even if it doesn't emit light because of its gravitational effects. There's also another effect, which is sort of the third thing that gravity leads to, which is, according to Newton, gravity could only be attractive. But in fact, in Einstein's scheme, gravity can actually be repulsive as well as attractive. The set of things that actually generate repulsive gravity are in a classification that we give the very scientific name of exotic. That simply means strange. There are no forms of matter and energy that we measure directly in the laboratory at this point, which are repulsive in terms of the gravity that they put out. But it is possible theoretically that they might exist. And in fact, we have looked into the universe, and again, we do see evidence of repulsive gravity, and that's because the rate at which the universe has been expanding has actually been increasing. So in fact, we would have expected attractive gravity to simply slow down the rate of expansion. That is, the rate at which the universe gets larger over time should start to decrease. But in fact, it's actually getting faster. So the rate at which it's getting larger for about 5 to 7 billion, the last 5 to 7 billion years, has actually been increasing over time, which means that there are exotic forms of matter or energy or both existing in the universe. So the answer to the question is yes, the expansion of the universe is accelerating. We see that through very powerful explosions called supernova, a particular kind of supernova called type 1a, but the name doesn't really matter. They're just really bright flashes of light that lasts for a long time because the star that explodes is very hot and it glows for roughly around 2 weeks to 6 months. And consequently, we can see the light from very, very far away. And we can measure how the characteristics of the explosion can be used to determine the distance away. Now, as I said, these explosions are very powerful. So you see examples of them in these pictures in which a single star exploding is putting out more light than the 100 billion stars that it shares the galaxy with. Okay, that's how powerful the explosions are. So from billions of light years away, we can measure the characteristics of these things. And in fact, they indicate, along with other tests that we can do, that in fact the expansion rate has been expanding over time. Now, the combination is that the amount of attractive gravity and the amount of repulsive gravity would indicate that there's roughly only 5% of the gravity that's out there that's measured is due to the stuff that's actually emitting light. So there's 20 times the amount of stuff that is exotic or is a form of matter that's not included by quarks or electrons, which is, as far as we know, what makes up all the stuff that's emitting light here. All the stuff that's in between, that's dark, is also producing gravity. Some of that gravity is repulsive. And consequently, we know that we don't have a complete picture with the standard model of physics, the particle physics model that explains the behavior of the quarks and leptons. So we refer to dark matter as the part of matter that's this exotic piece that is not explained by quarks or electrons. That's about, there's about 3 times as much of that as there is of the stuff that emits light. And then the rest is dark energy. Okay, that's about 70% or so of the stuff that's emitting gravity. So what we have to do is to do experiments that actually are able to study dark matter and dark energy. The way we do that is we have to study the gravity that's emitted by both, and we have to study that gravity by looking at its effect on the things that actually are emitting light that can be seen by our telescope. And so the idea is to map out at very high resolution the entire history of the expansion of the universe from its earliest times up until very recent times. And we do that by building a machine that is explicitly designed to examine the universe's history in exactly this way. This is a project that started in 2004. I'm still working on it. It takes first light probably in 2024. So some 20 years after it was first being contemplated. But it is contemplated to be the ultimate discovery machine because we understood enough about the history of the universe being the necessary thing to examine to understand this. So it's a project that's appealing to many nations. Pretty much every nation on Earth that does cosmology and particle physics will be attached to it. It will make maximal use of data by having the very latest techniques for data science and artificial intelligence included in how to analyze the data. It will have an impact beyond sort of just cosmology and particle physics because it will give us a complete compendium of everything in our solar system, including things that might actually eventually hit us and cause great damage. And it will include anyone who's interested in doing the science as part of the scientific community that's able to access the data and make use of it to make discoveries. The most important thing is that it will actually generate the questions for the 21st century and presumably the century beyond that, the 22nd century as well, because it will examine the most fundamental aspects of the universe itself. In this case, we are using the universe itself as the laboratory. The experimental measurements are the things that you see in the background emitting light. All of those are galaxies. And the determination of those galaxies and how they behave relative to one another over time is a determination of the expansion rate. And the expansion rate over the history, going back as far back as our telescopes can see, can be compared to exactly what we expect, again, through theory, where the theory now includes the theory of dark matter and dark energy, which we didn't have before. So that experiment is called the Virasi-Rubin Observatory. Here is a picture, which is almost a real picture, right? This is the image, but the actual image looks exactly like that, and I'll show you. Inside of the thing at the top is the Simone Survey Telescope, which is the most powerful camera ever devised for doing astronomy. Here is the real picture. Currently, if you go down to Chile, there's a mountaintop right at the end of the Atacama Desert, about 7,000 feet up, in which that telescope now exists. The camera is not there yet. It's actually traveling from California probably in about a month to go down to South America. I won't go through the numbers because we don't really have time, but as I said, it's the most powerful telescope ever built for astronomy because it has the most powerful camera ever built for astronomy. It uses what are called charged couple devices, CCDs, which are the same things that your cell phone uses to take pictures, except you can see the person here on the left holding the actual CCD for this. It's literally about 1,000 times larger than the camera that goes into your cell phone. And it's much more accurate in terms of its ability to determine the wavelengths of light. Why is this necessary? Well, again, we want to be able to take pictures that allow us to look at the smallest scales of the universe, but we want to take them in over the largest scales imaginable or capturable in terms of our technology. So what you see in the background is the Hubble Deep Field, so-called ultra deep field. And the thing about the Hubble is it's very powerful, but it can only see a very small part of the universe at a time. And so you have to basically take a lot of pictures over a long period, years, in order to build up the picture that you see in the background. If we talk about the camera that we're dealing with, which is called the Legacy Survey of Space and Time Survey, that will actually be able to see the entire picture that you see in the background at the same resolution of the Hubble in every picture. So we will be able to map the entire southern hemisphere roughly every 3 nights at the same or just about the same resolution as the Hubble telescope does for only a thimbleful of the universe at one shot. That's a huge amount of data. It'll be, in the end, roughly around 100 petabytes of data. So if you want to know something that is a comparable scale, the data set that Citibank uses for all the credit cards that it distributes all over the world for a period of about 5 years is about 100 petabytes. Okay, so that's every transaction literally made by hundreds of millions of people generates a data set over 5 years, which is about as large as the data set that we're going to generate from this telescope over a period of 10 years. So that's huge. I said we can see everything that goes on in the universe. So in our own solar system, we're going to find every asteroid and every comet that is above about 160 meters in diameter will be tracked, and we'll be able to determine which ones are actually eventually going to collide with Earth over some period of time. So we'll have advanced knowledge of what's happening. So there are 4 big things that are necessary for the scientific mission of this telescope. I won't go through them, but you'll notice that even though I'm interested in only one part of one piece of those, the dark energy and dark matter part, there are other parts that I have a personal interest in as well. It's simply that I'm not the expert who's going to be leading the science as part of that. But the STEM education piece is one of those. That is a fundamental piece of what we're talking about in terms of what this telescope will achieve that no other telescope has, which is that this is the first large observatory that was designed and built around sharing the data with the public and doing it in such a way that the public will actually be able to make its own scientific observations in addition to being able to use this for education, say in schools. So one of the things that I am doing to help with that is that I am part of a nonprofit corporation. I'm on the executive team here for what's called the LSST Corporation that is raising money through private philanthropy in order to create the next generation of astrophysics data scientists. That is, people who use very large data sets in order to study the intersection of particle physics and cosmology. This has been pretty much the province of only people who go to universities like Yale or Harvard or Stanford or Berkeley or Princeton. Literally around the world, there's only about 20 or 25 universities, and essentially 99% of the people who do the work that I do in terms of science got their PhDs at one of those 25 universities. We want to expand that enormously by, first of all, using the STEM education piece that has been designed into this telescope as the incentive, and use private philanthropy in order to make it possible to eliminate the barriers for people getting their education on the basis of doing this science. So we've succeeded with getting the first $15 million or so of that money. We've used that to form, sorry, it's so small here, to form an interdisciplinary network for collaboration and computing called LINC that is going to actually start last year and this year, producing fellowships for people who are going to be from a number of areas, not necessarily astronomy or physics. They might be computer science, they might be electrical engineering, they might be social scientists, but they're interested in the mission, which is understanding and exploring fundamental science for the purposes of delivering the best information as to the scientific story that comes out of that data to the community. And the community in this case is, again, all of the nations that are going to contribute to the science. So we will have all of the data accessible over the World Wide Web. We will have tools that are built by this LINC collaboration that will actually make it possible for anyone who has the interest at any age to actually get engaged in doing their own scientific research. You will be able to have a form of interaction that is very much like Google, in which you can ask a simple question: how many supernovas were discovered in the LSST dataset last night? That number will be somewhere between 10 and 50 every night. And you will simply be able to ask that question, create the database, get information at every level of detail that you might want to use it in order to make your own explorations as to whether or not those supernova are telling us something different than we've been understanding from the roughly 3,000 or so that have been discovered before. So this is a terrific project. I invite all of you to learn more about it. There's a website, www.lst.org, in which you can actually start to get involved with this even now. First flight, as I said, will be in 2024, and the mission will start for 10 years to examine every aspect of the universe's expansion history and so much more about the Milky Way and everything about our own solar system will be in this data set. All of this is coming from the first major observatory to actually be named for a woman astronomer, Vera C. Rubin, who you see here in a picture in 2002. So it's a really terrific way to get involved in what I expect will be a doorway that will be much broader, much more open to citizens around the world than has ever been possible before. So with that, I'll stop, and I'm happy to take any questions that people might have.
Okay, thank you so much, Dr. Gladney, for the presentation. It was very engaging and highly informative. We're now going to open it up for any questions. You can unmute and ask the question, or you can write your question in the live stream chat or the Zoom chats. And we're projecting this Q&A section to be about 15 minutes, depending on how many questions we get. Although due to tech issues, I know a lot of people weren't able to make the meeting, so we might cut down that time.
Okay, so at the beginning of the presentation, you talked about how like fundamental questions in physics led to modern technologies like GPS and cell phones. And could you like explain like a specific example from this?
Okay, so the World Wide Web, for example, began at a particle physics laboratory, CERN, in Switzerland. And it was explicitly designed in 1989 as a way to make it easy for particle physicists, which has always been a worldwide collaboration. That is, the last particle physics collaboration I was on had more than 1,500 PhD scientists from more than 30 nations working on it. So a number of different languages, a number of different time zones, and yet we all had to be able to communicate with each other very effectively just to write a single paper, for example. My name is on just over 700 papers now. Each one of those papers has roughly 200 to 1,500 names on it. And in order to get all those people to agree, you had to have a technology that made it possible for us to easily exchange information without having to worry about computer protocols. So the World Wide Web was designed explicitly to do that. So I used to be at the University of Pennsylvania for 3 decades. I was the person who managed the computer that was the first World Wide Web connection for the University of Pennsylvania. That was started in 1990. I was the first person to actually write Java in order to define web pages that came out of the World Wide Web, and that's because that's where it began. It very quickly, of course, found utility outside of particle physics, and so most people don't know that it was created by a particle physicist for particle physics research. For GPS, the thing that people, I think, don't understand is that GPS would not work at all. It couldn't possibly be practical without Einstein's theory of gravity. General relativity is absolutely essential to get the resolution of your position on Earth to a scale of around, right now, you can do 1.5 meters with just common equipment like you have on your cell phone. Okay, without general relativity, it would be roughly about 100 meters. Okay, without special relativity, it would be twice that. So you actually need something that people don't think about at all in order to make it possible for your car to tell you in 100 feet, you're supposed to make a left turn or a right turn, right? So it would be completely impractical without Einstein's theory of gravity in order to do the correction to the, I talked about cosmological redshift. Well, the radio waves traveling from a satellite to Earth are subject to Earth's gravity, and Earth's gravity distorts the radio waves enough that we wouldn't actually be able to use the timing difference between the satellite and Earth well enough to get the accuracy down to 1 meter without understanding what that cosmological redshift does. It changes actually time, the flow of time. So in orbit, the satellite flows about a microsecond slower in time than we do on Earth. And that's because in Earth, we're in a higher gravitational field, slightly higher than the satellite is. So again, you know, it's necessary to have these things that people don't think about. Otherwise, the technology would be completely impractical or would never have been created in the first place.
Adding on to like the practical applications of the research, do you ever think about those practical applications when you're researching, or do they just kind of come out of coincidence or like a different perspective by another person?
Yeah, it's a great question. So yes, sometimes I do. So for example, when I was at Penn, I had a student who, he was not a physics major, he was an econ major, actually. He was at Wharton. But he was very smart, and he wanted to take physics because he wanted something that was a little more challenging than economics. And so the question was, well, what should you work on? Because he wasn't really that interested in working on the stuff that I was working on for particle physics, but he was interested in the more practical aspects. And so we could go downstairs, literally 1 floor down, and the electronics group that was building things for the experiment that I was co-leading, was also building electronics for the next generation of PET scanners, right? So I don't know if you know what PET scanners are, but you've probably heard of MRI, right? So there's X-ray, there's non-invasive imaging through what are called magnetic resonance imaging. And there's another almost non-invasive technique called positron electron tomography, in which you use a small radioactive tracer that emits positrons. We don't have antimatter anywhere around nearby. And so something that emits positron is easy to detect no matter where it is, close to a detector that's explicitly set up to look for the radiation that comes when positron, which is antimatter, annihilates with an electron. It turns out that, again, timing turns out to be the most precise way in which you can determine where the radioactive decay producing the positron happened to be. And it turns out that you can, for example, put some of this radioactive material into glucose. If you inject that into your bloodstream, your brain uses an awful lot of glucose in order to carry out the tasks of thinking, right? It uses an awful lot of energy. Glucose is essentially fuel for how the brain operates. So if you want to examine a tumor, what you do is you inject a little bit of this radioactive material in the form of glucose. It passes the blood-brain barrier. It gets absorbed, and the tumor tends to be burning a lot more energy than even the nerve cells in the brain around them, which are also burning a lot of glucose. So you give a little bit of time, and then you can locate where a lot of glucose is being, by virtue of the fact that it's being absorbed there very quickly in order to fuel the tumor cells that are going on. So the question of how precisely can you determine the depth, that is, you can see the XY position, but if you want to know how deep into the brain it is from the surface, depends on how accurately you can do the timing. And we, in particle physics, were making the best timing electronics possible. And so there was a company in Germany that was basically paying our engineering team to determine the best means of doing the not only determination of the accuracy of the electronics for determining the depth, but also making it easy to set up a scheme for how you would produce those electronics. That is, nobody made those kinds of electronics. We were producing them custom. And so you also wanted to determine ways in which you do a design that is easy to manufacture. You can turn that over to an electronics company, a semiconductor manufacturer that is actually able to produce a chip that can then be put into a PET scanner that is sold by a company in Germany all around the world. So he worked on that project for almost a year and a half.
Regarding your favorite unanswered question slide, what's your favorite question that you want answered, and what's your reason for it?
Well, really, dark energy is the most mysterious stuff we have. It's the only form of energy or matter which we've ever seen that is exotic, that produces repulsive gravity. So I would say if we tried to get down to an understanding of all of those questions, I'm of the opinion that we won't be able to answer any of them completely until we answer the question of what dark energy is and where it came from. And that's because dark energy is the one thing for which our theories have no clue how to include it. Dark matter, we have some idea where dark matter might come from. It's not included in any of our theories right now, but there are ways in which we could expand those theories. The math allows us to include something that would allow us to have a description of a quantum field that would produce particles that have dark matter properties. But dark energy is completely mysterious. It might actually be something that is fundamental to space itself and doesn't have anything to do with fundamental quantum fields. Right now, there's only one thing that we've ever observed that has that characteristics. It's called the Higgs field. It is a property of space itself. It has nothing to do with any other form of matter, except that because it exists everywhere in space, all forms of matter communicate with the Higgs field. And the communication is what leads to mass, right? So the fact that anything has any heft or weight to it is due to the fact that there is the existence of this field, which is fundamentally a part of space and time itself. We think that dark energy has a possibility of being a second field exactly like that. And if that's true, then we don't have complete answers to any of these other questions until we have included that second field as a part of our quantum theories for explaining matter and energy. So that to me is the biggest question that's still unanswered because we don't have any clue of how to include it in the theories right now.
In the chat, Kevin Dang also asked, for aspiring future astrophysicists, what would you recommend the first topic they learn from this subject to be?
Well, I think that's really tough to answer because you don't really have easy ways to learn about the topics in the subject. If you study physics, the kind of physics that you're going to study, and I started in 7th grade, is rolling things down inclined planes, right? Or measuring springs and determining the formulas that apply to how strong a spring is compared to how far it's stretched or compressed. So it takes a long time, many years, to get to the point where you start asking the questions that I put on the slide. So if you want to get engaged in this, the easiest way to first learn about it is to, first of all, as I say, there are websites that can tell you a bit about what the LSST is doing. There are comparable ones for the JWST, for example. And you begin with that. And then on the web, because so many people are starting to, and have been for a while actually, writing information as to what the science is and how we write it and how we go about examining it. You can start from those web pages to get a glimpse into the subject matter that you want. In the end, the one thing that's going to be common to all of them is math, right? And so no matter how much math you take, there will always be more math that could be used that's applicable. But I would say the second subject that is probably going to be like math and that is ubiquitous right now, and I only see it becoming more so, is data science. So you have to learn a computer language. This semester, I'm going to be teaching graduate students basically how to use Python in order to do scientific projects. And so I would say you want to take a language, any language, computer language, and you want to get to the point of some degree of mastery with it, because all of the science that we're talking about now requires us to write new kinds of programs that haven't been written before. Machine learning, for example, is one of the most powerful approaches we have for handling very large data sets. And consequently, you have to have some familiarity with how to use computers to answer questions in order to be able to learn the things that are necessary to get engaged in the science directly. So hopefully LSST, through its STEM education piece, there is a design part of the project, which is what makes the best educational tools. It's possible I will have someone working for me as a postdoc next year who's going to take up, again, explicitly that issue about what's the best way to introduce to students of all ages that are new to the field how to make use of these computational tools that we're going to be producing in order to get engaged in research in the fastest possible way, right? So I don't know, right? He and I are going to talk next week, and we'll see whether there's a good match to his project. But you know, he's a PhD, master's degree in education and not in physics. He has an undergraduate degree in physics, actually. But he's one of the people that's interested in understanding how we produce new scientists who can actually produce new science. And so, to me, that's also an important question that has to be answered by people of the current generation, which is how do we get more ideas and more people producing those ideas into the field.
I had a question regarding, it's kind of just like a broad question about the subject of physics, but towards the beginning, you were talking about how like physics is kind of like a reductionist subject where we want to kind of analyze things for their basic parts. And then as we gain more information, apply what we know about our small subset to a larger field of information. And then later, you also mentioned about the accelerating expansion of the universe. And my understanding is that one implication of that is that there are kind of like regions of the universe that we'll never really be able to observe. And I was kind of wondering how that kind of fits into like a possible limitation on a complete theory if we can't apply our principles to those parts of the universe.
Well, it's a very interesting question, right? And so, yes, there are parts of the universe that have expanded beyond our horizon. So we'll never be able to see those, right? We're pretty sure that they're there, but the size of the universe right now, we would talk about the universe being 13.7 billion years old. And so you might think that that means that the universe is 13.7 billion light years across. In fact, it's closer to 100 billion light years across. We will only be able to see that part, which is 13.7 billion years right now away from us, or less, light years away from us or less. But again, even the parts that we can't see, if we've got enough consistency in terms of how the theories work, and they lead to something that is unified from a logical point of view, that is, we see that every question that we ask seems to be answered within this one series of logic. We don't have to make exceptions. We don't have to put in kludge factors or things like that. Then I think we have a pretty good confidence that those parts of the universe that we don't see or never will see must be operating according to the same rules. I think there's a fundamental aspect of the philosophy of this, which is important to keep in mind.
Decide that you want
and
to
it's been
help
true for
other.
particle physics for a long time. When we build an experiment, how do we know that we're seeing all the particles that are there? Okay, can our accelerators be making things that our detectors aren't designed to see? And that's a great question. And the reason why we know that there aren't particles being produced is that if we take the contrary and say that there are, then it means that those particles don't couple. That is, they don't interact with any of the stuff that is matter as we currently understand it. And if that's the case, then it means that it's not physics that actually affects the universe. Like, the universe is made of matter. And so if you have some kind of physical phenomenon that doesn't interact with that matter, well, it's true, we will never discover it, but it also doesn't matter, right? I mean, it doesn't actually have any impact because it doesn't interact with the matter that we can actually see and experiment on. So while it's possible there could be things happening out beyond our horizon to see, those things can't impact what we can see. And consequently, you can ask, how important is it to know that that's actually going on, right? Philosophically, there might be a question that you would have that you could say is incomplete. But in fact, it's a question that's not a well-posed question in logic, because you have no way to actually answer it, right? It's equivalent to saying, can God make a rock that he cannot lift, right? Well, there is no logical answer to that, because it requires you to either defy one definition or another definition. And consequently, those two definitions themselves are incompatible logically, right? So if there's parts of the universe that impact our universe, we should be able eventually to see what that impact is. And that gives us a hint as to what's going on in the part of the universe that we can't see. If there's stuff that's going on out there and it has no impact whatsoever on what we can see, then yeah, we won't know about it. But it doesn't have any scientific merit as something to study.
So earlier you talked about how gravity bends light, causing distortion. And I was wondering how you can measure the extent of the distortion, or like determine the pre-distorted state of the celestial objects.
Yeah, so that's a question of statistics. So I have to write down some equations for you to actually go through the proof. But the point is that there are correlations. If you remember that picture, and I could show it again, it wasn't just that the images of the background galaxies were distorted in shape. You notice that there was also kind of a circular appeal to how that distortion was taking place. So again, it's very much like the bottom of a wine glass, which you guys probably don't don't have a lot of experience with looking through, but if you look through, the distortion looks very similar to the distortion that is predicted by general relativity. So the question of how we unpack that picture is exactly based on that, right? In other words, if I were to show you an image and and the image is distorted, but I show you what the original image is like, then you would be able to mathematically work out exactly how the distortion changed from the original image to the image that you see that is distorted. But we can also work that the other way around, right? If we know what the bottom of the wine glass is, we can map its geometry, then we can also undistort the image and produce the original image pretty accurately, right? And again, by statistics, we can determine how well we've done that. So there is an error or a degree of uncertainty on how well we've reproduced the original image on the basis of how well we understand the geometry that general relativity describes for the stuff that's in between. So luckily, we've got two different ways of doing this, right? We can look at that circular distortion as one kind of distortion, and then we can look at the stretching of the shape, that is the size, which is the amplification. The amplification also depends both on how strong the gravitational effect, the gravity is, and also depends on the distance between the stuff that's producing the gravity and the background image. So those two can be played off against each other mathematically to come up with a really good undistorted image of what the background looks like. And that we can compare to pictures, again, for stuff that's equally far away, but not affected apparently by some gravitating thing that's in between us and them. So those two pieces of information together can give us a pretty accurate picture about how much stuff there is, at least in terms of how much gravity it's producing, and also can give us an idea of the shape of the gravitating stuff. So it doesn't have to be a regular shape. It still is going to tend to have a circular distortion, but the degree to which the circular distortion is a little bit more distorted over here as opposed to over here depends on whether or not the object producing the gravity is oblong or is itself really compact. So it's math. It's a lot of math, but statistics we understand really well. So it's math that's been worked out over centuries. We're pretty sure it works extremely well. And again, we can actually test it. As I said, we can take an optical image where the optical image exactly reproduces what general relativity produces because the math appears, in this case, luckily, just to be the same in terms of the result. And consequently, we can work out pretty well what the undistorted image must look like.
I just want to ask, so you mentioned you grew up in a religious household, but later
Mhm.
rejected religion as an answer to those fundamental questions. Would you be willing to expand on the intersection of religion and science? Because I've seen some scientists like completely reject religion, while others kind of use it as like a parallel like motivator to their research.
Yeah, so you're going to get a different answer to that depending on who you ask, right? So my PhD advisor was very strongly religious, still is, and didn't find any conflict between the work that he did as a particle physicist and his religious beliefs. You know, he was an elder in the church and so forth. So for him, he's able to have the two pictures of how you answer these questions be consistent. For me, it wasn't possible for them to be consistent, but mostly because in the question that you ask in religion, you get to the point where people say they're not interested in having the answer, right? So who cares how the universe began? We kind of know how people began, and that's good enough, right? We don't really need to know how old the universe is. So they were not interested in using religion at all to try and explore the answer to that kind of a question. But for me, it makes a big difference, right? If you kind of say, was it really, you know, if we talk about the Judeo-Christian foundation for how the universe began. It was 6 days, right? Is it really 6 days, or were days actually used as a metaphor for a much longer period of time? For me, asking that question seemed kind of essential. But again, for the people that I grew up, I was missionary Baptist, which is what happens if you're Black and from the South. But that in and of itself wasn't a question of exploration, right, or of thinking about whether or not there actually are answers to that question to be found, say in religious literature or in history. And for me, that was unacceptable, right? So you can either live with it and say, okay, well, there's certain ways in which those questions are answered by science, and there are other ways in which they're not answered by religion, or they're answered only to a certain level, and you're going to be satisfied with that, or not. For me, again, I don't know whether science is ultimately going to answer those questions either in my lifetime, but it at least it's making the effort, right? And that to me was important.
Are there any further questions? All right. If that's it, then that's all we had for you guys today. Thank you so much, Dr. Gladney, for taking the time to inform us about the work that you do. I'm sure you have a very busy schedule, so we really appreciate it. The information was really fascinating and insightful. For everyone else, thank you for attending today. I hope you all enjoyed it and got to learn about Dr. Gladney's work. I, for one, am really fascinated by the LSST, and I'm looking forward to the first light and the breakthroughs it will bring. Thank you so much and have a great day.
Thank you. Bye.
Recording stopped.